So today lecture will be on concept of transformation rate between two equilibrium states. We have now we to understand how transformation rate between two equilibrium states, how they are defined with respect to thermodynamic factor as well as kinetic factor. Already we learned that rate it's depending upon the kinetic factor as well as thermodynamic factor. And in this lecture, we will further understand the relationship in more analytical way. Analytical means there should be a mathematical expression and as well as there should be a physics-based interpretation of the mathematical expression. So in order to understand this kind of phenomena, we'll start with the assumption. Now we are assuming a process going from one state to another. And when the process is going from one state to another, it is going through or passing through a transition state. And you can also define such kind of transition state and individual initial state or final state based on quantized energy states. So, and another thing we should understand that the number of particles distributed over the quantized level can be described using Boltzmann equations. So, in this lecture, what we are going to touch upon? We are going to touch upon how the kinetic factor and thermodynamic factor are controlling the rate of a particular transformation process from one equilibrium state to another equilibrium state. And how the process is occurring? We are assuming that the process is going from one equilibrium state to another equilibrium state via passing through a transition state. So if you see in the picture, there is a one plot where initial state, final state, and in between there will be a transition state and different energy level for the different state are given. Now we have to understand that there is a difference and there is a interrelationship between kinetics and thermodynamics. But how to use the two concepts to describe the chemical reaction or metallurgical transformation, phase transformation, or any kind of process that like carbonization, doping, whatever the metallurgical process. If you want to do heat treatment, you have to transform the phases, get the customized microstructure in order to get desired properties of a material. So now question is that how to use the two concepts to use the and thermodynamics in order to describe the chemical reaction or material transformation regarding transition state, driving force, activation energy. We have to see the diagram. If you see the diagram, you will understand that initial state, there will be an activated state, and initial state, from initial state to reach the activated state, you have to have a activation energy, and from activation energy when you reach, you can cause the barrier, and there will be a driving force, that is the energy difference between initial state and final state, that is del G. Here I have written. Now let us assume that the system in all states, initial, transition, and final, can be modeled by a linear harmonic oscillator. Now we try to get the analogy with the harmonic oscillator and the behavior of this kind of transformation between two equilibrium states. So now let us assume the system, all the states of the system, namely initial state, transition state, and final state, to be modeled by a linear harmonic oscillator. So if you see in the picture also, if you see in the picture also, the right hand side to me, that picture, there is a state 1 and state 2, and in that picture you can see that E10, that is the state 1 zeros, this is a 0 point energy, and slowly you can get the different quantum state, and EC0, there also you are getting different quantum state. So EC0 or E20 are the 0 point energy. Now we have to understand what is 0 point energy. Beforehand, we should know that should be energy levels, and that can be quantized at I equal to 0, 1, 2, 3, and can be written as EI I plus half into h nu. And where h is the Planck constant and nu is the vibrational frequency. This is known to us. Now, when t equal to 0, then all frozen to lowest level, that is called I equals to 0. Then you can tell that is the 0 point energy. What is the value? E0 half h nu. And then you can understand that slowly each state have a different quantized energies level. Quantized energy level. It's a very obvious as per quantum physics. Now we are going to understand that at different states as ith state, ith quantized level, EI equal to E0 plus I h nu already written in there. And from the three states, if you identify that ith level of individual state, then what will be the expression you can get for the state 1, state 2 and transition state? That E1I equal to E10 I h nu 1 and E2I E20 I nu 2. Then transition state will be ECI equals to EC0 plus I h nu c. So in this way, you based on the 0 point energy of each state, you can identify the next level of quantized state or level of quantum state. Why you are doing? We want to understand that what is the requirement of energy from state 1 to state 2 when they are passing through the transition state. So now the particles to go from state 1 to state 2, they must have energy excess of EC0. That we understood. Must have this minimum energy. That is actually, you can tell, the barrier for the transition state here has to cross. So that actually can be understood from the quantum physics approach what we are introduced here. It's a very little bit of quantum physics. Now we are going to understand that for a particles to go from state 1 to state 2, they must have energy in excess of EC0. Now, using Boltzmann distribution, the fractional number of particles in state 1 having energy in excess of EC0 can be given by the expression written in this. If you see the expression, you can understand that how you can represent the functional particles in a state 1 having the energy of excess of EC0, because there you have to understand in the transition state the 0 point energy is required minimum excess energy, and in the state 1 certain particles will having higher level quantized states that maybe crosses the EC0. So we have to find out the fractional number of particles. It is just a population analysis. Fractional number of particles in state 1 having energy in excess of EC0, and it can be expressed by the expression you can easily understand. Now, if you go certain mathematical calculation, then the expression will be looks like N1 of C by N2. N1 by C by capital N1 equals to e to the power minus EC0 minus E10 by KT. And that actually known as a Boltzmann factor. And here the constant K is known as or represented as Boltzmann constant. So similarly, different way you can represent. Similarly, the fraction of number of atoms in state 2 having energy excess of EC0 can be represented by n2 small n2 of C by capital N2 equals to e to the power in bracket EC0 minus E20 bracket complete by KT. So in this way you are getting two fractional number. Now if you correlate with the probability concept, then what you understand that N1C small n1 small n1C by capital N1 is actually thermodynamic probability for a system to go from 1 to 2, means here state 1 to state 2. So it is a thermodynamic probability. Why we are telling that is a thermodynamic probability? Because here you are having different energy state, and based on the energy state you are trying to understand that the number of particles having higher level of energy, they are having a chance to cross the barrier. So you are looking at the probability of, and that probability based on the energy criteria, and that's why we are looking at thermodynamic probability. Although we are talking about activation energy barrier, you have to understand activation energy barrier as per till date our understanding is related to kinetics, but here we are looking at the different quantized state. So that's why thermodynamic probability of a system to go from state 1 to state 2 can be defined by small n1 of C by capital N1, and vice versa. You can tell that n2 of C by capital small n2 of C by capital M2 is a thermodynamic probability of a system to go from state 2 to state 1 if we are looking at reverse process. So in this way you can understand that there is a thermodynamic probability parameter can be calculated based on Boltzmann distribution constant. Now we have to correlate with the this probability whatever we have derived. We have to correlate with the rate of the transformation process, and that transformation is occurring from one equilibrium state to another equilibrium state. Until now we are having a very good concept of what is equilibrium, that we understood from previous lecture. So now we are going to correlate between rate of the transformation process of one equilibrium state to another equilibrium state with this kind of probability things. Now suppose if you want to understand the net forward process rate, how it is correlated with the probability factor. So what will be the rate is varies small n1 of C by capital N1 minus small n2 of C by capital N2, because this is the resultant of thermodynamic probability of a system going from state 1 to state 2, and the reverse, the thermodynamic probability of a system going from state 2 to state 1. So that resultant will give the rate of forward process rate. It's a very obvious. So from that, if you put the expression, then e to the power minus in bracket capital is C0 minus capital E1 0 by KT minus e to the power minus capital EC0 minus capital E20 by KT. From that, and if you do certain mathematical calculation, then what will be the rate expression? The rate expression will looks like a capital A, that is a constant, you can tell rate constant, into e to the power minus in bracket is capital is C to the power 0 minus capital E1 to the power 0 by KT. In the second bracket 1 minus E capital E to the power 0 minus E2 to the power 0 by KT. Here 0 prefix in the superscript the 0, you can tell that it is representing that 0 point energy, the energy at T capital T equal to 0 is absolute scale. And C in the subscript is representing transition state. In subscript 1 is representing the initial state, and subscript or state 1, and subscript 2 is representing state 2. So note that for rate greater than equals to 0, that is progress going from state 1 to state 2, what will happen? If you want that forward reaction is occurring, but it's happening, that forward reaction process is occurring. Forward process is occurring from state 1 to state 2, then the rate must be greater than 0. Then the term 1 minus e to the power minus E1, capital E1 0 minus capital E2 0 by kt must be greater than 0. So now we are going to understand that, okay, in order to get the forward process, rate must be 0. So that criteria also can be imposed in an expression like 1 minus e to the power minus capital E01 minus capital E02 bracket complete by kt. K is the Boltzmann's constant. That must be also greater than 0. Now let's say we want to define two terms. To not define, we want to understand and want to represent two terms. That is activation energy and change in internal energy. What is there already in there in thermodynamic concept? So let's define del A, that is activation energy is C0 minus E10. And I already several times told that 0 is representing energy at 0 Kelvin or T equal to 0 absolute scale temperature. And then another is as the change in internal energy from state 1 to state 2. That is represented in the slide. Now then for a rate greater than 0, what we have to have? We must have del U less than 0. Change in internal energy must be less than 0. So negative change in energy. Now you can express the rate equation such a way you can now see there will be a kinetic factor, there will be a thermodynamic factor, and the constant A is proportional to the vibrational frequency. So now from the start of this lecture or previous lecture, we told that rate is depending upon two factors, kinetic factor and thermodynamic factor. Now we are getting the equal sign in between that rate and these two factors. Means we are now mathematically expressing, analytically we are expressing the concept. What we are presuming physics-based understanding there. Rate must depends on kinetic factor as well as thermodynamic factor. Now things are going so much ahead. We are now able to make a mathematical expression. We are getting a mathematical expression where equal sign is there to equate between left hand side, that is rate, and right hand side, that is a certain expression which is representing both the factor, kinetic factor as well as thermodynamic factor. And if you see what is kinetic factor, is only energy based, or another is activation energy based, activation energy barrier based. So in this way, till now we learned that rate is depending upon two factors, kinetic factor and thermodynamic factor, and analytically or mathematically that can be expressed in a equation that can be told that rate expression. Now we are going to consider two extreme cases to understand the physics-based interpretation of that mathematical expression of rate of transformation process between two equilibrium states. Okay, if the mod value of internal energy much less than K multiplied by T, the temperature absolute scale, then what will happen? E to the power del U by KT is almost equal to 1 minus del U by KT. That can be understood from exponential sum expression, series expression from class 2 concept, and approximation based on the criteria. Mod value of del U is much less than K multiplied by capital T, that is temperature in absolute scale. Then you can derive the next equations. Here you can see that e to the power activation energy barrier by minus activation energy barrier by kT in the bracket minus del U by kT. So in this way, you can see if there is a small change in energy. So when the energy changes are very small, means internal energy changes are very small, del U much less than kT, then the process generally is a thermodynamic control process. Okay, because here you are looking at the feasibility, the rate in the rate constant or rate expression. Also you are seeing that process is basically depending upon the how small change is occurring. And we know when we are talking about slowing state or controlling state, we used to talk about that minimum step with a minimum driving factor. So here you are looking at that small, very small internal energy change. So thermodynamic driving factor is very minimum, and that's why it will occur or not. It is based on thermodynamic. So it is a thermodynamic control process. Now just you take another extreme case where the change in internal energy or energy that del U is much greater than kT. That is Boltzmann's constant multiplied by temperature in absolute scale. Then what will happen? E to the power del U by kT much less than 1 and del U also less than 0. In this case, the expression will looks like a rate A into e to the power minus activation energy by kT. No del U term because del U is much bigger and is much bigger than kT. So from the approximation, you can tell that e to the power del U by kT is much less than 1. Means it's very small value. So now the process is becoming kinetic control. Although I have not written in the slide, I want that you should understand, think why it is the kinetic control, because it only depends upon the act. There is your activation energy barrier, the process activation energy barrier is very important. When the transformation is highly favorable with respect to thermodynamic criteria, that is the difference between the energy from state 1 to state 2. You are getting very lower energy from going from state 1 to state 2. But the activation energy barrier is a very significant amount. At that scenario, you have to tell that, you have to understand that kinetic control process, then the transformation process is basically kinetic control process. So as a whole, what we are now understood, if such a scenario when the large energy change is associated with the transformation from one state to another state, in such a case only kinetic factor is important. In other words, you can tell that the reverse rate is negligible and the net forward rate equals the forward rate. Okay. Now all those things we understood. We are trying to get the analogy, try to get the system where the constant temperature, constant pressure, what will happen with this kind of rate expression, that we will learn from next slide. In general, at constant pressure and temperature, we use Gibbs energy to replace the internal energy and use R to replace the Boltzmann's constant K for the units per mole. Then what we have? We are having A multiply, or here C is the constant, C is multiply, A and C is I have used interchangeably. So both are same. So A or C is multiplied by e to the power minus del G EA by RT into del G by RT, when del G is much less than RT. That it is analogy to extreme case 1. And if you go for extreme case 2, the analogy is e to the power jelly RT and del G much greater than RT. So what we till now our conceptual take away from this lecture. In thermodynamics, The Helmholtz-Free is a thermodynamic potential which measures the useful work obtained from a closed thermodynamic system, which at a constant temperature and volume. That we know that it is a closed thermodynamic system, that is Helmholtz-Free is useful for that, and when the system is at constant temperature and volume. For such a system, the negative of the difference in the Helmholtz-Free is equal to the maximum amount of work extractable from thermodynamic process, in which the temperature as well as volume are kept constant. Under this condition, we can say, you can think, you just try to think and understand. Under this condition, it is minimized at equilibrium, and the Helmholtz-Free is a very good concept and very beneficial concept for understand the work obtainable from a closed thermodynamic system at a constant temperature and pressure. On the contrary, if you want to understand the utilization or significance or importance of Gibbs-Free in thermodynamics, Gibbs-Free is a thermodynamic potential that measures or determines the useful for the process initiating work obtained from an isothermal, isobaric thermodynamic system. Isothermal means temperature will be constant, isobaric means pressure will be a thermodynamic system. When a system changes from a well-defined initial state to a well-defined final state, you have well-defined means all the thermodynamic parameters with respect to energy criteria, you know about that system. So defined well. So when a system changes from a well-defined initial state to a well-defined final state, the Gibbs-Free, that is del G, is equals the work exchanged by the system with its surrounding minus the work of the pressure forces during a reversible transformation of the system from the same initial state to same final state. These understanding are very important. Now we try to compare with this concept with Helmholtz-Free. So if you compare to Helmholtz-Free, the isobaric restriction on Gibbs-Free is inconvenient for some kind of application. If you are going to apply to some cases, you can take an example. In explosive research, there is an explosion. Helmholtz-Free is often used since explosion reaction by their nature induce pressure change. There is a, what we told, isobaric restriction is there in order to apply Gibbs-Free concept. You have to understand. Now you are looking at for a research area where explosive cases, some explosion occur, and you want to understand what is the reaction thermodynamics or reaction process, reaction mechanism or reaction thermodynamics. Then Helmholtz-Free is very important. It is very useful since explosion reactions by their particular nature induce pressure change. That there will be a change in pressure. So then how can you apply Gibbs-Free concept? And on the other hand, another example, if you can take, Gibbs-Free often defined as the chemical potential that is minimized when a system reaches equilibrium at constant temperature and constant pressure. As such, it is a convenient criteria to understand spontaneity of the process with constant temperature and pressure. So we have understand that how thermodynamic factor and kinetic factor are strongly correlated in order to understand the rate of a transformation process from one equilibrium state to another equilibrium state. That is very important. Today's lecture is completed. Thank you.